All right, let's talk about the invisible force that runs pretty much everything. It's the reason an apple falls from a tree, right? But it's also the reason entire galaxies don't just fly apart. We're diving into the universe's ultimate architect, gravity.
So think about this for a second. What's keeping you in your seat right now? And what's keeping the Earth orbiting the Sun? It's a simple question, but the answer is just massive. It's the same exact phenomenon doing both jobs. So how does one single principle manage to run the show on a personal scale and a cosmic one? Well, let's unravel the story.
Our journey starts with probably the most famous aha moment in the history of science. You know the story. There's an apple, a tree. But the idea it sparked, that was anything but simple. It was about to completely redraw our map of the universe. So let's get into the genius of Sir Isaac Newton.
You know, science is really just one long conversation that spans centuries, and you can see it perfectly right here. It all starts with Aristotle, who pretty logically thought, hey, heavier things must fall faster. Makes sense, right? But then, centuries later, Galileo comes along and says, hold on, and he shows that if you ignore air resistance, everything falls at the exact same rate. But the real game changer, the masterstroke, that came from Newton. He saw that apple fall, and he made a connection that nobody had before. He wondered, if the apple's falling, is the moon also falling?
And the conclusion he drew from that one question was just profound. This wasn't just some rule for apples or moons. Nope. Newton said this force of attraction is universal. That means you, me, the planet, the sun, every single particle that has mass is constantly pulling on every other particle. It's just a fundamental property of the universe.
And Newton didn't just stop with the idea. He gave us the math to prove it. This beautiful little formula tells the entire story. The force of attraction, F, depends on the mass of the two objects. That's m1 and m2, literally how much stuff they're made of. And you divide that by the square of the distance between them, which is that r. So the more massive things are, the stronger the pull. The farther apart they are, the weaker it gets. And that g out in front, that's the universal gravitational constant. Think of it like a cosmic conversion factor that makes the whole equation work no matter where you are in the universe.
Okay, now look closely at that distance, the r, because it's not just r, it's r squared. And that little number 2 has a huge impact. So just think about it for a sec. If you take two objects, like two planets, and you suddenly move them twice as far apart, how much weaker does that gravitational pull get? It drops to just 1/4 of its original strength. This is called the inverse square law, and it's a huge deal. Because that distance is squared, distance has this outsized effect on gravity. If you triple the distance, the force plummets to 1/9. This is exactly why you feel the Earth's gravity so strongly, but you don't feel the pull of Jupiter. It's a core rule for how the entire universe is put together.
All right, so we have this universal law that governs everything. But how does that actually play out in our daily lives? Let's bring things back down to Earth for a minute and look at how this law gives us concepts we deal with all the time, like acceleration and, of course, weight.
So this brings us to something that trips a lot of people up, but there's a really great way to think about it. The difference between big G and small g. Big G is the universal constant from Newton's big formula. Think of it as your true friend. It's the same here, it's the same in the Andromeda galaxy, it's the same everywhere. It never changes on you. But small g, that's the acceleration you actually feel because of gravity right where you're standing. It's your fake friend, because its value can change. Here on Earth's surface, it's about 9.8 meters per second squared. But on top of a mountain, it's a tiny bit less. And on the moon, it's way, way different.
And this leads us right into another classic mix-up, mass versus weight. It's actually really simple. Your mass is the amount of stuff you're made of. It's constant. It's the amount of you. Your weight, on the other hand, is not constant at all. It's just a measurement of how hard gravity is pulling on your mass.
And here's the perfect way to picture it. Let's say you take a trip to the moon. The amount of you, your mass, is exactly the same. You haven't changed a bit. But the moon's gravity is only about 1/6 as strong as Earth's. So what happens? Your weight, the force pulling you down onto the lunar surface, would be just 1/6 of what it is right here. You'd feel incredibly light. You could jump super high, but you would still be the exact same you.
Okay, so for more than 200 years, Newton's law was it. It was the final word on gravity. It just worked. But then, in the early 20th century, this young patent clerk comes along and decides to completely rewrite the rules of the universe.
So let's step into the incredibly mind-bending world of Albert Einstein.
What Einstein proposed with his theory of general relativity was just staggering. He said, what if gravity isn't a force at all? He suggested that it's not some mysterious pull between objects like Newton said. Instead, Einstein's idea was that massive objects don't exert a force. They actually warp and curve the very fabric of reality itself, what he called spacetime.
Now, here's the classic way to get your head around this. Picture a big, flat trampoline. That's spacetime. Now, take a heavy bowling ball, let's say that's our sun, and place it right in the middle. It creates this deep curve in the fabric, right? So now, if you roll a little marble, let's call that planet Earth, nearby, what happens? It doesn't get pulled towards the bowling ball. It just follows the curve that the bowling ball made in the trampoline. And that, according to Einstein, is gravity. It's just objects moving along the curves in a reality that's been bent by mass.
So whether you think of it as Newton's invisible force or Einstein's warped reality, the end result is the same. Gravity is the master architect of our universe. It is the sculptor responsible for all the massive structures we see when we look up at the night sky.
And if you want to feel just how powerful gravity is on a planetary scale, check out this number, 11.2 kilometers per second. That is Earth's escape velocity. That is how fast you would need to be going and keep going to completely break free from our planet's gravitational pull and never come back. Anything less than that, and Earth's invisible tether will always pull you back down.
And really, its influence is absolutely everywhere. Without gravity, stars and whole galaxies would just fly apart into nothing. Planets would just shoot off into deep space. The very air we need to breathe would just float away. Even the tides in our oceans, which are caused by the moon's gravitational tug, they just stop. It's the silent, constant force that creates order out of what would otherwise be total chaos.
So we end up right back where we started, with a question. Newton gave us the rulebook for gravity, and then Einstein came along and showed us that the game was being played on a curved field. It really makes you wonder, if something as fundamental as gravity is actually a warp in reality itself, what other huge cosmic secrets are just hiding in plain sight, waiting for the next person to look at something simple